We continue our discussion on signal conditioning and signal processing. In the next few slides, we will discuss on how we do the digital analog signal conversion. Let's try to revisit first what is the difference between digital and analog signal. Most signals that we see normally are analog. What is analog signal? I think it's pretty a common understanding about what the analog signal is. Analog signal is basically a continuous signal, right? That always varies in time, and it's why do we say it continuous? Because the value in it is continuous, right? It's always giving a continuous value for non-disrupted time in here. But in real practice, when we are going to record signal, including in analog signal, we need to discretize it. Let's take a look on this slide. Some signal are digital. Well, the simplest example of a digital signal, if you are listening to your music from your cell phone, all of the data stored in your cell phone is digital, which means every signal it is discretized in order to store in binary value in your cell phone. So if you look at this example of an analog signal where the signal is continuous here, when you want to record it and store it in digital format, let's say the one that I just mentioned, the music in your cell phone, it's stored in digital format, or music that is stored in your compact disc, it's in digital format. The signal, the analog signal, has to be discretized first. What do I mean by discretized? So you sample it at a regular interval. So if this is your signal, I redraw it again here. We discretize it, we sample it at a certain interval, and then you just record the value at the time and the instances where you sample it. So in this case, after you discretize it, you only have this discrete value. Right? Of course, the shorter the time interval, the more resemblance your discrete signal to the analog signal. That is pretty intuitive, right? After you discretize it, how do you store all of these discrete signals in your device, your cell phone, let's say? The signal is stored in digital manner. So what do I mean by digital manner? After you discretize it, you have this signal at this point of the sampling signal, and then what the value in between of this interval is kept constant, it's hold. So when you sample it for the first time, and then you hold it until you arrive at the next sample time, and then you record this point, and then you hold it until the next one. You come to this point, you record it, you hold it, and so on and so forth. So you have a stair-like signal in here. But of course, if you look at this digital signal, the point might not really coincide with the real analog data here. Why? Because the value that you record here is also discretized. So you only record at the point which is, because it is discretized like this, so it only records the point which is the closest to this real analog signal. So in here you will have this first is a stair-like signal, and then the true value might slightly different than the analog signal due to the discretization of your recorded value. So you have two discretization manner: the discretization in time, the discretization also in the value that you want to record. So that's how digital signal is recorded in your device. If you are wondering about the leakage, then the signal will leak. Some information are missing, that's right. Same like when you move from analog to discrete signal, what happened in between sampling time here is missing. You don't have this information, the information between the time when you sample signal. And then when you move to digital signal, you will lose another information where that is attributed to the discretization of the y-axis. Okay, so that is different of analog, discrete, and digital signal. The ideal signal is, of course, is the analog, but we cannot record analog. Well, we can. In the past, we record everything in analog manner when you are referring to tape, cassette, video player. In the past, I don't know, perhaps it's not your time anymore. In the past, you have a cassette, you have a video tape. Nowadays, everything is stored in digital manner using CD, or it is stored digitally in your cell phone, in your computer. Okay. Let's take a look again a bit detail about this digital signal. Just an additional information that I want to share with you. Like what we have discussed before, if you have analog signal and you digitalize it, right? You sample at a certain interval and then you hold the value in between of this interval, and you also discretize the y value. At the end, you will have a stair-like signal, stair-step signal, approximation of the original analog signal. Okay. As I have already mentioned also before, the more sampling that we have, the better the accuracy of the digital signal to the analog original signal, right? To digitalize the analog input, analog signal, yeah, we can also use an op-amps in a circuit arrangement that we refer to as sample and hold amplifier. If you look at this circuit diagram, basically if you look at the op-amp part here, this is just a simply voltage follower circuit. Okay, where V naught here is the signal that we are going to record and digitalize. S here represent the switch to regulate the sampling interval. Okay, and the difference between this circuitry to the voltage follower is the additional capacitor here. Perhaps you can guess already here that the capacitor is meant to hold the signal at every interval, to hold the signal when you want to convert from discrete to digital signal, the one that we just mentioned in the previous slide. Okay, let's take a look here on how this sample and hold amplifier work to digitalize an analog signal. As I have already mentioned before, this point is connected to the signal that we want to digitalize. Let's say, for example, this is the signal that we want to digitalize and to record. And then this function here, as you can see here, represent how I regulate the switch S here. So the green part here represent the instance when I close the switch, when the switch is connected, when this line is connected, and then when S is equal to 0 represent when the switch is open, right? Which means that when this line is disconnected. And then I sample it using this switch in a regular pattern like this, on, off, on, off, on, off. and so on and so forth. So to make our analysis easier, I redraw again here the instances when the switch is on and when the switch is off. Yeah, so the green uh, area there represent the instances when the switch is on. Now let's take a look. When the switch is on, when this line is connected, there is a voltage coming from this signal, so from this analog signal that we want to record. And then since this is connected, of course, this amplifier will just work as a voltage follower. In such, during this instance, when the switch is connected, this counter or the output of this op amp will just follow the actual analog input signal. But after certain interval, I remove the connection, I open the switch S, and then this will be disconnected, so there is no current flowing in here. But during the on period, this capacitor had been charged. So when this switch is open, even though there is no current flowing in here, but there will be a current flowing from the charged capacitor. What is the voltage flowing from the charged capacitor? Of course, we will have a constant voltage. So when this switch is off, then there will be a current flowing here, where the voltage here basically is the same as voltage, the last voltage when this is charged. So when during this off period, we will have a constant voltage here until we close again the switch. In this region and these instances, when the switch is closed, the output of this op amp will again follow the analog signal until again the switch is off. And then the voltage will be halted here because the voltage here will receive the positive input terminal will receive the voltage from the capacitor until again the switch is closed again, and then it will follow the signal, the analog signal again. This will happen repetitively until we complete the signal. So this, the red bold line here, basically is the signal that will be recorded by this circuit. If we regulate the on-off switch following this pattern. Now let's try to change the sampling time, the interval here. I made the interval to be shorter here, but everything is the same. So what will happen if we use this interval in regulating the switch S? Same like before, right? This is what we will get when the switch is on. The output of this op amp will follow the input voltage, the input signal, and when switch is off, the output will hold the last voltage. Again, when it is on, it will follow again on and off, then it will follow the regulation of the switch timing. Okay, so this will be the signal. Well, somehow we can say at this point that the faster the switching time of the switch S there, the closer the output signal from the op amp to the original signal, right? But this is still not good enough here. So what I'm going to do here, I change a bit how I regulate the switch. How I do it, I just do it following this arrangement. What do these green arrows mean then? Well, same like before. These green arrows represent the instances when I keep the switch on. But if you look at this, the switch is closed only in a very short period of time. So I close the circuit, the switch, I close the switch, and then I open it, I disconnect it for certain duration, and then I switch it on again, but I switch it on for a very short period of time, and then I disconnect it again for a certain period, and then I on it again for a very short time, and then I off it. On, and then off. On again for a very short time, and then off. I do it that repetitively. So slightly different than the one in the previous case, where the duration of the on switch is the same to the duration of the off switch. In here, the duration of the on is very short, while I still keep the duration of the off switch slightly longer, same like before. In such, if I regulate the switch S in this manner, basically what it is passed to the op amps, this point, this point, this point, this point, this point, and so on and so forth. Just at the instance when I close the circuit, when I set the S on. So these are the voltages that is passed through these op amps once I regulate the switch following this pattern. Okay, and then now what? What will happen to the output voltage V naught? Of course, during the off period, because of the capacitor, the voltage will be held, right? And then this is what we will get. After this, the voltage is halted, and then it moves here, halted again, moves here, halted again, and then this what we will get, right? So that's how we digitalize an analog signal. How the analog signal at the end will appear in a state-like form. It's because, again, it's because same like before, I regulate the switch S, but I regulate it in this following manner. I just keep it on for a very short time and then let it off for certain period of time. That I do that iteratively. So this is how we sampling it in time, but this is not the end of the story of this digitalization of an analog signal. The next story that I want to share with you, the digitalization is not only in terms of time. So we don't digitalize it, we don't discretize it in time, but we also discretize it in the signal itself. So instead of having a continuous value in here in which you can record at any point here, apparently in analog to digital circuit, it only records at a certain interval as well. So as we have already mentioned at the beginning, the discretization in this digital signal is not only happening on the time axis, but also in the y-axis there. So how to digitalize it? Well, this is pretty straightforward. The signal then in y-axis, it will only be recorded at the closer value, the discretization of the y value. Before we discuss about that, I think I need to recall our memory again about the binary numbers, because everything, when we are talking about digital signal, everything is recorded in binary way. So what is binary numbers? If you compare to decimal number that we normally use, we recognize 10 symbols, right? From 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 1 to 9. Okay. So we have 10 symbols there to represent any numbers. But imagine if we only have two symbols, 0 and 1. What happened to decimal number? We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then that's all. We run out our symbol. So when we move to the next numbering, we go back to 0, but we add the next digit in front of it. So it will be 1, 0, which is 10, and then again 1, 1, 1, 2, 1, 3, until 1, 9. We round out the last digit symbol, and then we move to the second symbol. So it will be 2, 0, which is 20, 2, 1, 21, 22, and so on and so forth. Until 19, we round out the symbol. Okay, we add one more symbol at the beginning. It will become 1, 0, 0, and so on and so forth. That's how the concept of numbering in decimal format there. So same like that, we do the same concept, but we only use two symbols, 0 and 1. So after 0, we have 1. After that, there is no more symbol because we only have 0 and 1. So we move to the next symbol. We add one more digit in front of it, 1, and then we start it again from the first symbol, 1, 0, 1, 1. We run out the symbol, we add one more digit in front, 1, 0, 0, and so on and so forth. Okay. So if you take the relationship between decimal number and binary number, and then you will see that 0 will correspond to 0, 1 correspond to 1, but we don't have 2 here, so the next number is 1, 0. So 1, 0 in binary correspond to 2 in decimal, 1, 1 is 3, and so on and so forth. Okay, so that's just to refresh our memory again about binary numbers. I believe you know about this already. Now this is the one that I just mentioned, to how to correlate decimal and binary. 0 in decimal is 0 in binary, 1 in decimal, 1 in binary, but 2 in decimal, it becomes 1, 0 in binary. I don't call it 10 because it's not 10. 3, it's 1, 1 in binary, 4 is 1, 0, 0 in binary, and so on and so forth. To calculate it faster, then you can use this trick. So if you want to convert 6 in decimal to binary, what will happen? 6 in decimal will be equal to 0 times 2 power of 0 plus 1 times 2 power of 1 plus 1 times 2 power of 2. So it will follow this pattern: 2 power of 0, 2 power of 1, 2 power of 2. That's why 6 in binary number will be equal to 1, 1, 0. Okay. Same to 37, it will be equal to 1, 0, 0, 1, 0, 1, because 37 is equal to 1 times 2 power of 0 plus 2 times 2 power of 1 plus 1 times 2 power of 2, 0 times 2 power of 3, 0 times 2 power of 4, and 1 times 2 power of 5. So it becomes 1, 0, 0, 1, 0, 1. That is 37 in decimal. If you look at this, this is normally what we call as 6-bit binary number, because we only have 6-bit arrays there. Okay, and if we have a binary number that limited only to 6 digits, and such we only have 6 array binary number like this. The first digit, we call it as MSB, most significant bit. The last digit here, we call it as a least significant bit, or LSB. Why do we call it like that? It's simply because these represent the least number, right? 1 times 2 power of 0, which is equal to 1. And the first digit here represent to the highest number in this arrangement, which is equal to 2 power of 5. That's why we call it most significant, and this one is least significant bit. Now, if you go back to the signal after we discretize the time, the y-axis, the value of y-axis apparently is also discretized when you record it in a digital format. How the discretization will happen, it depends on the capacity of your storage. Let's say we are talking about your phone, then it has a certain storage. If let's say you only have 3-bit array system, so 3-digit means you only have 0 in binary, which correspond to 0 in decimal. You have 1, and then you have 1 0, you have 1 1, you have 1 0 0 1 0 1 1 1 0, and 1 1 1. Okay, and 1 1 1 in binary corresponds to 7 in decimal. So you have from 0 to 7 numbers. If you have 3-bit array binary, then in decimal you can store from 0 to 7. You can store 8 numbers from 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7. You have 8 numbers then. So that means you can store, you recognize 8 numbers. But 8 numbers, the first one is 0, right? So basically, then you only have 7 interval there. If you have 3-bit arrays, then you only have 7 interval. From 0 to 7, you only have 7 interval. 0 to 1, 1 to 2, 2 to 3, 3 to 4, and so on until 6 to 7. You only have 7 intervals there. That means the resolution of your y-axis, if you discretize it with 3-bit array system, the resolution will be equal to 1/7. You only have 7 resolution. You only have 7 7 ranges that will discretize your y value. So this is an example that will help us to picturize the problem here. Let's say we have a measurement system, and the measurement system, the y value, the output of this measurement system has a range from -5 to 5-fold. So the range is 10-fold, -5 to 5. You have 10-fold range. But then you will discretize it with 8-bit arrays. 8-bit mean you will have interval only 2^8 - 1, while the range of your measurement system is 10-fold. So that means then the resolution of your system will be 10-fold divided by the number of intervals, 2^8 - 1, which will be equal to this value. As we have already discussed on how to digitalize an analog circuit before, in the next few slides, then I will discuss with you on how to convert it back. Why do you need to convert it again? Same like what we usually do hearing music from our cell phone. The data, the signal that is recorded in your cell phone is digital, but now you want to listen to the music that you hear should be an analog signal, right? Because you want to hear the nice music again. So after you record it in a digital signal in your device, and then when you want to give an output again, if you want to read it again, if you want to observe it again, what you have to record it, the recorder, the recorder of the signal should be able to present it again to you as if it is an analog signal. So we need to convert from digital back to analog. How to do that? We use a digital to analog circuit. Well, perhaps you sometimes hear about the term of D to A. So digital two analogs. They are abbreviated normally as a D2A circuit. So this is one example of D2A circuit, which is called as weighted resistor network. So how does this circuit works? It's pretty straightforward actually. We connect all of the bits of our digital signal. So digital signal is each of the digit, each of the bit only has 0 or 1 value, right? And then we tap each of these digit here. We pass it through this pin from the MSB, the most significant bit, to the LSB, the least significant bit, one by one. And then each of them we connect it to the following resistor. Let's say in this example, let's say we have a 4-bit array digital signal. We want to convert it again to analog signal. So what we do, I connect all of this bit to series of different resistor where the difference of the resistance value for each of the resistor is doubled. So let's say if the first resistor, the resistance is R, the second one will be 2R, the third one is 4R, the fourth one will be 8R, and so on and so forth. But let's take a case when we have only 4-bit array case here. I connect the MSB to the lowest resistant resistor here. So I connect the MSB to R, and then the LSB obviously to the resistor with the highest resistance value. Okay, I put all of these 4 resistors in parallel, and then I connect it in series with a load resistor. Then what do I do? From each of them here, from all of this bit here, it will give a discrete voltage, only 0 or 1, so only on and off. But then what I expect in this output voltage, the output voltage is measured from the two ends of this load resistor. I would expect an analog signal from there. How does it work? So let's take a look in here. This is just again the interpretation, the circuit interpretation of the previous diagram that you saw before. So the MSB is connected to resistor R, the LSB is connected to resistor 8R, and S2 to 2R, S1, what I mean by S2 is the second most significant bit to R2, the third digit from the most significant bit to 4R, and so on and so forth, right? But we only have 4 bits here. And then what? Let's say I have a value equal to 0 from the most significant bit, 0, 0, 0, 1. So the least significant bit is 1. The rest are 0, which means this in decimal, it's equal to 1, right? So 1, 0, 0, 0, so it's 1. The least significant bit is 1. The rest are 0, so in decimal is also 1. So what will happen to the current here? If only the S0 that is connected, if I have 0, 0, 0, 1, so S0 is on this S0 that is connected, so the current will flow through this route, right? The voltage is VR, the resistance is 8R, so the current will be voltage divided by resistance, so it will be voltage divided by 8R. On the other hand, let's say if I have 1000 in decimal, then 1000 will be equal to 2 power of 3 will be equal to 8 in decimal. So this will be on, off, off, off. So the current will flow through this route. So the current will be equal to VR divided by R. the I, the current will be the highest because the R is the smallest, right? VR over R, that is the current. In the previous case, when we only have S naught that is on, so we have VR divided by 8R, the I will be, the current will be small, right? Correspondingly, if any of these switches are closed, then you will have different current. If all of them are on, then the current here is just the superposition of the current flowing at each of the resistance when one of them is closed and the other are open, right? So again, when everything is on, then the total current will be equal to the summation of this. S not S1, S2, S3 here, even though it give a notation of the switch, but you can see this as the bit. When it is on, then S naught will be 1. When it is off, then S naught will be 0. Same thing to S1, S2, and S3. Okay, so this is the simplest way to convert digital signal to analog signal. So once we have this weighted resistor network, normally again, this is the story that we have discussed before. The output from your digital sensor, output of the sensor might be too weak. So normally the output of this D2A circuit will be connected to an amplifier to amplify the voltage output there. But there are a few disadvantages of this weighted resistor network. First one, I rarely see this weighted resistor network is used more than for 6-bit encoding. So at most, I only see it for 6-bit application. I guess the reason is related to the second disadvantage, because it's difficult to find wide range of resistance in the resistor. Imagine if in the previous case, if we have a 4-bit case, you need 4 different types of resistors. The one resistor with a resistance of R, 2R, 3R, and 4R. If you have, let's say, 16-bit case, then you need to have R, 2R, 4R, 8R, 16R, 32R, and so on and so forth until you have 16 resistors. So it might cause another difficulty. That might be the reason why I never, if I can say, I never see a weighted resistor network to be used on more than a 6-bit case. Okay. So these are some disadvantages of weighted resistor network. As an alternative then, for digital to analog converter, we use this network, we use this circuit, the circuit that we use to call it as a R2R ladder. So how does it work? In here, the nice thing of this network, the first thing that I can mention, and you can immediately see, you only use 2 types of resistor, R and 2R. Okay, and then each of the bits, each of the digit in your binary code is connected to this branch. Okay, from MSB, the last one, and then LSB to the first one. Okay, but then how does it work? When one of the bit is on, then this branch, let's say if this bit, if MSB is on, is active, then this switch will be connected. So this connected switch represent the active bit. So if S3 is active, that means the MSB is active there, and so on and so forth until the last bit. But then how does this R2R ladder will convert the digital signal to analog signal? Let's take a look on this analysis. So again, I have, just for simplicity, let's just consider 4-bit array of digital signal here. We can analyze this R2R ladder by using Thevenin technique. You still remember about Thevenin, don't you? You can just play again the previous video if you have already forgotten how to use Thevenin technique to analyze electric circuits there. So again, let's go back to here. The arrangement is like this. The first resistor, the first 2R resistor is what we call is terminating resistor here, is connected to the ground, and each of these point, the end, one of the end side of the 2R resistors is connected to different bits of the binary number there. Now let's see what will happen if we have 0001 signal in our binary signal, in our digital signal. So 0001 means it's only the LSB is only the least significant bit that is active. So this is connected. It is energized, it is active. The rest are connected to the ground. It's off, so it's not connected here. So what will happen? How this will be converted to analog signal? Let's analyze it step by step. Let's try to analyze this part first using Thevenin technique. So what I'm going to do here, I just take a look on this part, right? This red box, because I want to analyze this part as a Thevenin, and for time being, I just consider this as a load to my Thevenin box. So let's take a look on this. What we have to do, we have to derive the Thevenin voltage and the Thevenin impedance, right? Let's try to check what the Thevenin voltage will be. If you look at this, we have a voltage source, which basically this is the voltage source from the LSB, right? Because the LSB is on, so this is connected. We have a voltage source here. We have a voltage source for time being, let's just call it VR. Even though in practice, the LSB will only have two values, 0 or 1, right? But to make it general, let's call it VR here. VR is the voltage from our digital signal, right? So this is VR. We have two resistors, 2R and 2R. So basically, if you look at this circuit, this VR is connected to these two resistors in series, right? VR, 2R, 2R. So 2R in serial connection is connected to the voltage source VR. That means the Thevenin voltage, the voltage at these two ends, right, is following the voltage divider rule, right? Luckily for us, these two resistors have the same value, 2R, 2R, so the Thevenin voltage will be just spread evenly between these two resistors. So this will be half of VR. The voltage in here will also be half of VR, but our interest is only for the voltage in here. So the Thevenin voltage, the voltage between these 2 points is equal to half of VR. That is our Thevenin voltage. What will be our Thevenin impedance? If you still remember how we do it in Thevenin techniques, we just short circuit the voltage source, and then we calculate what is the equivalent resistance between these two ends. If you look at this, we have two resistors where each of them has a value of 2R connected in parallel, right? So we can analyze the equivalent impedance, equivalent resistance between these 2 points. You know how to do that, but I think you also know if you have two resistors sharing the same value connected in parallel, the equivalent resistance will be half of each of the resistance. So the Thevenin impedance here will be equal to R, half of this resistance. Okay, this will be our Thevenin circuit, Thevenin equivalent. So then I can redraw this circuit by replacing this red box with this Thevenin circuit. So it will become like this, where this part basically is this Thevenin circuit. Okay, let's move to analyze this equivalent. So this I redraw it again here. This is the equivalent. After I analyze the first Thevenin, and then now I will analyze it again using Thevenin circuit. But I will look at this box and then I will analyze the Thevenin equivalent of this red box. So what will happen? Again, this looks the same like before. We have 2R. This first 2R is coming from the serial connection of these two resistors with a value of R. So 2R, I have 2R in here, and then I have the voltage source here. But the voltage source follows the Thevenin voltage in the previous slide, so it will be equal to half VR. Now, let's analyze the Thevenin equivalent of it. The voltage, the Thevenin voltage of this, same like before. We will have a voltage divider circuit. We have a voltage source of half VR, and then we have two resistors of 2R connected in series to this voltage source, right? So when you want to find the voltage between these 2 points, will be just again just follow the voltage divider rule. The voltage between these 2 points then will be equal to half of this voltage because these two resistors share the same resistance. So the Thevenin voltage again will be half of it, so it will be equal to quarter of VR over 4. What about the Thevenin impedance? Same like before, we just short circuit it and then we have two resistors connected in parallel. The equivalent resistance will be equal to R, half of each of these resistors. So my Thevenin equivalent will be like this, right? Voltage, the Thevenin voltage is quarter of VR over 4, and the Thevenin impedance is equal to R. I will redraw again this circuit, but I will replace this red box with this Thevenin equivalent, right? So this is what we will have. I do it again, I analyze it again for this part, but I will use this part as my Thevenin circuit. Same like before, this is what we will have. You can analyze it. The Thevenin voltage will be equal to VR over 8, same like before, but we will still have the same Thevenin impedance equal to R. So this will be my Thevenin equivalent, and then I will redraw this diagram again, but replacing the red box with a Thevenin equivalent. Then I can analyze it again further. Well, this will be the end of my series of Thevenin. So this I can analyze it again as another Thevenin circuit. But now my Thevenin equivalent will be like this, where the voltage source or the Thevenin voltage will be equal to VR over 16 with again the same Thevenin impedance equal to R. So this is equivalent to my 4-bit digital to analog circuit with a input value of 0001. That means when the value is 0001 and I pass it through this R2R ladder network, the output voltage of this network will be equal to VR over 16. This is what I will record as an output voltage. Now let's take another case. What if I have 0010 in my digital input here? 0010 should correspond to 2 in decimal number, right? In decimal system. So previously, in the previous slide, when we have 0001 correspond to 1 in decimal number. So 1 in decimal number, the voltage output from the ladder network will be equal to VR over 16, if you still remember. Now let's take a look what will be the output of this ladder network if the input is 0010. So you can do exactly the same like before. You can analyze it using Thevenin method. You analyze it first for this one, right? If you analyze for this one, then you can replace this part as this Thevenin equivalent, where the Thevenin voltage is equal to half VR. And then again, you analyze again this part using Thevenin equivalent, and then you will get this at the end. So this will end our Thevenin analysis. So at the end, what you see here, the output voltage of this Thevenin equivalent, the V naught here will be equal to VR over 8. That means when the input of this digital signal is 0010, what you will read from the V naught from the output of this ladder will be equal to VR over 8, 1/8 of the VR. Same thing, what if you have 0100? This will not give anything, so I analyzed this using Thevenin, and this is what we will get. We have half VR as our Thevenin equivalent, but we still have 2R here. I analyze it again, what will be the output voltage from this Thevenin equivalent. The output voltage V naught will be equal to quarter of VR. I leave it to you to analyze it. You can do it, but we just simply follow what we did in the first case, the case of 0001. So again, back to this, if we have a digital input of 0100, then the output voltage will be equal to quarter of VR. Same thing, when we have a case of 1000, then the output voltage will be half of VR. So again, to summarize it, when we have 0001, we have VR over 16. When we have 0010, we have VR over 8. When we have 0100, we have VR over 4. And if we have 1000, we have half VR. So what will happen? Anything in between, if let's say we have 1010 or we have 0110, it's just simply superposition of all of the 4 cases that we just discussed. So if all of them are active, let's say we have a value of 1111, then the voltage that will be given by the output V naught here will be just summation of all of them. 1/16 of VR plus 1/8 of VR plus 1/4 of VR plus half of VR. So in here, S0, S1, S2, S3 represent the digit from the least significant one to the most significant one. Okay, so that's how to analyze the R2R ladder network, and then you can extend it to any number of bits. It's not only restricted to 4-bit digital number. You can extend it to 16, 32, 100, or any number of bit easily without any problem, because what you need is only two types of resistor with R and 2R. What is the value of R? You can choose it by yourself, as long as the second resistor has a resistance value twice of the first one. Okay, so this is nice thing of R2R compared to the previous circuit. I leave this to you to try it by yourself. You can try to analyze it by yourself. What will be the output of this R2R ladder when the digital input is 0, 1, 1, 0? You know, from the previous discussion in the previous slide, you can just take a superposition of the output 0, 1, 0, 0 and 0, 0, 1, 0. So it will be just a superposition of a quarter of VR plus 1/8 of VR, then it will be equal to 3/8 of VR, right? 1/4 plus 1/8 is 3/8, so 3/8 of VR. Definitely this will be the output, but I suggest you to try to analyze it using Tiffany method. There are a few more slides that I want to discuss with regards to the measurement in digital form. This is related to what we usually refer to as aliasing phenomenon. Aliasing occurs when we record a signal, but the sampling rate of the recording is too coarse, where the sampling rate is less than the Nyquist frequency. What is Nyquist frequency? Nyquist frequency is twice of the fundamental frequency. You might have another question then, what is fundamental frequency? In short, then, fundamental frequency is the frequency of interest in your measurement. So let's say if you want to measure a signal that the frequency is around 5 Hertz, let's say. If the frequency of the signal that you want to measure is 5 Hertz, that means the Nyquist frequency is twice of that, so it's equal to 10 Hertz. The sampling rate of your measurement should not be less than 10 Hertz. I will give you a more detailed insight about this concept of aliasing, but just to give you an overview on what aliasing looks like, sometimes you might see probably when you are looking at a helicopter, the blades, the propellers of this helicopter, which is rotating at very high speed. Sometimes when we see these rotating propellers, sometimes we have a notion that the propellers or the blades is rotating in a much slower speed. Or sometimes we might have a notion that the propeller is rotating slowly, but in the opposite direction. You might also see the same phenomenon in wheels of a car. When a car is running at a high speed, you might have a notion that the wheel of the car is rotating in the opposite direction or rotating in the same direction, but it seems that the rotation is very slow. That is one example of aliasing effect. This slide, I guess it will give a detailed insight on what really happening in aliasing phenomenon. So I have a video here that I prepared before. It's not really a video. Actually, this is an animated movie. What I have here is a wheel that is rotating at a certain speed. It is an animated movie. So if I run this video, you will see that this wheel is rotating at a certain speed in a clockwise direction. Let's run the video. Okay, you will see that the wheel is rotating in the clockwise direction in a certain speed. And as I have already mentioned before, this is an animated movie. It's an animated video, which means this is a collection of few pictures of the wheels in different orientation. And then after I arrange these pictures frame by frame, and then I animate it. So if I take a series of the pictures of this animated video frame by frame, it will look like this. So these are the pictures frame by frame. This is the first frame, second frame, third frame, and so on. If you look at this from the first frame and the second frame, the difference is only the second frame, same wheels, but it is the orientation is slightly different. It starts to move in a clockwise direction at a certain angle. And the third frame, you will see it is rotating more in a clockwise direction in another angle. So if I put this picture one after another and then I run it, so it looks like this wheel is rotating in a clockwise direction like what you see in this animated movie, right? But now, okay, let's take a look again on this series of the picture that I took frame by frame of this video. Now, what I'm going to do, I will reconstruct the animation again using these pictures, but I will skip one frame at every snapshot. So here, those pictures that I indicate with a red box here are the pictures that I will use to construct the second animated movie. So I will only use this, this, and then I put it as an animation here. I put it here, so this will be the second animation when I only take the alternate pictures. Okay, now I will run the video. What do you see? To me, when I see this animated movie, I have a notion that this wheel is rotating in the counterclockwise direction at different speed. So if I run the first video, it is rotating in a clockwise direction. The second video, I have a notion it is rotating in the counterclockwise direction, but at a lower speed. Even though I use the same pictures, frame by frame pictures, but for the second video, I just take every alternate pictures. And then that what happened. So why is it like that? This picture will give an illustration on how the aliasing effect happened. So here, the red signal here is the original signal. Let's say it's the original signal that I want to capture with my device. And then to capture this red signal, I use a sampling rate which corresponds to this point. So I sample this red signal with this sampling time. So I sample it only at this time, at this time, at this time, at this time, and the interval is always the same. So I always capture it at this interval. And then when I capture it only at those interval, this what I capture, the black dots are what I capture. Having these black dots, when I try to reconstruct the signal, what I normally do, I just connect dot by dots, right? And then if I connect dot by dots, what will happen? I will get this blue signal. Instead of getting the information of this red signal, I only get the blue signal. Where the blue signal, if you see from this picture, it's much, much less in the frequency. So that is basically what is the reason behind this aliasing effect. It's because the sampling frequency is much lower than the frequency of the signal we want to capture. So in short here, the philosophy here, when you want to capture a signal, when you want to digitalize a signal, or in other words, if you want to capture a signal in a digital manner, you have to be careful in choosing the sampling frequency. The sampling frequency cannot be too low, because if it is too low, you might end up into a wrong interpretation of the signal. Like what is illustrated in this slide, you might have a notion that the signal has too much lower frequency than the original signal, right? So in one side, we cannot take the recording at a very low sampling frequency, but of course, on the other hand, you don't want to capture original signal with a frequency that is too high. The result will be very good, of course, if you sampling it at a very high frequency. But on the other hand, you don't want to do that because it will be too expensive in terms of the storage. You will need a big storage for that. In terms of the infrastructure, you need a very sophisticated recording device, because the recording device has to have a capability to record at a high frequency. The next question is then, how do we avoid the aliasing effect? We will discuss this in a more detail in the next video when we are talking about filtration. But in short, what we are doing is, when you are recording a signal, you have put a filter to get rid of any possible signal that has a frequency much higher than the frequency of your sampling. Let's say if you want to measure a signal, but your signal contains many frequencies, you have to apply a filter that can filter the component of the signal that has high frequency. So you will not be able to measure the high frequency in your recording. The information of high frequency signal will not be captured by your device. Of course, you cannot capture it. You don't have the information of the high frequency signal, but at least by filtering the high frequency signal, you will not have a wrong interpretation of the signal that you record. Like what we see in the previous slide, when you are trying to record the red signal, eventually what you have is what you get is the blue signal, and then you might have a wrong interpretation that the frequency is much lower than what it should be. In that case, it's better to not record it at all, isn't it? Okay, then this slide concludes our discussion in digital signal.